Hello, my name is Anak Wanpasyeong, Group 5. I'm going to present deep learning. So let's go overview. So we're going to talk about what is deep learning and history of deep learning. Why is deep learning important for the future? Types of deep learning, compare deep learning to alternative options. Application of deep learning, challenges and limitations, future researchers of deep learning. And what is deep learning, right? So by definition, deep learning is subfield. Deep learning is subfield of machine learning concerned with algorithm inspired by structure and function of the brain, called artificial neural networks. So you can see on the right hand side, those are common structure of deep learning. As you can see, they're going to be input layer and then multiple hidden layers. In this, it only show 2, then output layers. Deep learning is subfield of machine learning, and is also a subfield of neural network. It's actually a type of architecture of neural networks. So the different types it different from all the types of AI because it can learn pattern from the input by solving optimization problem, and it can learn over time. It can fix its own problem, it can correct itself in a way, so it's like a human. And now I'm going to discuss about the difference of how deep learning learn versus how human learn towards the end of the presentation. And why is and deep learning is pretty good when dealing with a large number of data, because it has a simple architecture that allow the network to learn over time. Therefore, if it's more data, it means better learning in general. But sometimes when data become too big, too large, too complicated, the solution become intractable by current technology, by means of technique, hardware, for example. And deep learning, the word deep comes from just the deep neural networks. It's just deep because there are multiple hidden layers, like I mentioned before. And next up, we have history of deep learning. So I'm going to go by year because I feel like it's more like a development of deep learning. So I'm going to go by year, and you can see how deep learning, this field, come together. It's developed from different field, maybe computer science, mathematician, physicist, or biologist, for example. So in 1943, the first mathematical model of a neural network is created by Walter Pitts, who is a logician, and Warren Markov. They both published a logical calculus of idea immanent in neural activity. They proposed a combination of mathematics and algorithm that aim to mimic human thought process. The model is called Markov-Pitts neurals, which is still currently used today. Not in terms of use in practical term. I mean use the same name as before. And in 1950, the prediction of machine learning, it's from Alan Turing, who got famous from solving Enigma encryption from Germany. So in 1950, Turing proposed a machine in his paper named Computing Machinery and Intelligence, He also proposed a test called imitation game, or we currently now call Turing test, to determine whether a computer can think. So he claimed that if machine can carry on a human conversation for about 5 minutes, the machine is said to have passed. However, many still debate the validity of the result. This is very interesting because on Turing starts asking, okay, why do we need to decide whether or not how can we decide whether or not a machine can think? So he, instead of asking that question, he constructs a test that, you can answer it yes and no, whether or not if you passed it or not, which I find very interesting. And then 1952, first machine learning program. Arthur Samuel created a program to play checker. The program was unique in that it can learn and get better every time, and also correct its mistake. Now you can see here, this is the very fundamental of deep learning, the idea of learn by itself. So that's the first demonstration, successful demonstration of this types of program. Excuse me. 1957, setting the foundation of deep neural network. So the paper, the perceptron, the perceive and recognizing automation, was published, and it was the perceptron is a very, very fundamental of deep learning. So as you can see here, if I follow my cursor, you can see here, that's the what we call perceptron. You can see that there's going to be just input and then output. There's no comparison to this. There's difference. There is no hidden layer. So that's what perceptron is. Yes, and also what's interesting is that Frank Rosenblatt, who is the author of the paper. Sorry if I pronounce it incorrectly. He created the perceptron without using programming a computer. He used electricity and magnetic field to construct this type of experiment, which I find also, again, very interesting. And now you can see, again, this does not come from the computer science background or field. They are the combination of a lot of field over almost 100 years. And 1959, discovery of simple cell and complex cells. And again, this is also another point I talked about. This is the discovery of simple cells and complex cell heavily influenced artificial neural networks. So because deep learning, the goal is try to mimic how our human brain works. So the more we know about our brain, we can implement this understanding into the architecture. 1960, control theory. Henry J. Kelly published Gradient Theory of Optimum Flight Path in the paper. The paper is in control theory. It started that the behavior of a system with inputs and how it behaves modify by feedback. So now I start to understand how machine may be able to learn, even though this is, again, not about deep learning. So this idea later on is going to be developed, the basic understanding of backpropagation model. 1965, the first work in deep learning. First deep learning network was created. It was straightforward multi-layer perceptrons. computer identification system alpha successfully demonstrate learning of a computer, even though in this case there is no feedback involved, so no backpropagation because it haven't yet discovered. 1979. And also, if you guys are confused about the term, in the next slide or later on I'm going to discuss about types of deep learning, and I'll get into the terms that we in deep learning used. 1979, 1980, and ANN learned how to recognize visual patterns. So ANN, which is stand for Artificial Neural Network, Neoconitron successfully learned how to recognize visual patterns, for example, handwritten character and other recognized pattern like natural language processing. Now I want to also focus on something here. Say successfully learn how to recognize. It's not actually recognize patterns. It's not actually learn to recognize the number itself, but this is learn to recognize the pattern within each of the picture or handwritten digits, for example. So these idea, the project led to development of CNN, which was based on the way humans perceive image from our eyes. So CNN is a type of neural network, and again I'm going to get into it. CNN stands for convolutional neural networks. 1982, the creation of Hopfield networks. This is not per se a development of deep learning. This is development focused on a kind of a deep learning architecture. Excuse me. So here Job Hopfield creates RNN that serve a content addressable memory system, which means that content addressable memory system means it's a matching of input data to the stored memory. So now we start to use memory to learn, which is again very interesting. 1986, improvement in shape recognition and word prediction. Zohr problem. I believe that I haven't put this in here. Maybe I did. Yes, I did. So here is a big step of deep learning, because deep learning in general is not per se deep learning. It's perceptron cannot actually solve Zohr problem, which is a supervised kind of problem. So what was this? Zohr is a nonlinear separable, which is a kind of problem that perceptron cannot solve. Perceptron can only solve linear separable problem. So also, even though it's not capable of doing so, but there are some successful architecture model of perceptron that's designed specifically to solve this task and successfully done. But that's it's not generalized. So now the way how we fix this problem is by using backpropagation. And around this time is also the time where first backpropagation was created, from the paper Learning Representations by Backpropagation Error, which is help solving, like I said, nonlinear separable problem. Now the problem that deep learning can solve have a wider range from just one algorithm, backpropagation. 1998, learning to read handwritten digits. Now that's, like I said earlier, before 1979 to 1980, that was they recognized the visual pattern, but now they recognize the handwritten by using CNN and backpropagation. 1993, a very deep learning task is solved. This is also a very big step forward of deep learning. It used RNN to create more than 1,000 layers. Before this, the height, like 1989, it's only used 7 layers to solve hand-rigid problem, but now there's 1,000 layers, which can solve, 1,000 layers of RNN networks, which also a step forward of the complexity and ability of neural networks. 1997, LSTM. This is a kind of RNN. It eliminates the long-term dependency problem, meaning it allowed long-term memory to be lost, and is not used for when it's not used for a long time. Now it looks even more like our brain now, because it allows the machine to forget something. 1998, gradient-based learning. Jan LeCun, which is a rock star here, still currently pretty popular, published gradient-based learning applied to document recognition, paper in 1998, stochastic gradient descent algorithm combined with backpropagation algorithm now has become, from the paper, has become a very common way to do deep learning. 2009, launch of ImageNet. Now this is after about 2009 or so. It's going to be the development of modern deep learning. So through 2009, Fei Li created ImageNet, a very large and free database for more than 14 million labeled image. She make it free for the first time, like a very large neural network for the first time. This helped pushing deep learning forward. Like I said, deep learning depends largely on the quality of data and the amount of data. Especially, label image are pretty significant in supervised learning, which was the main focus of deep learning. 2011, creation of AlexNet. So AlexNet was pretty successful between 2011 and 2012 because it won several international machine and deep learning competition with its own creation, right? The AlexNet, which is a type of convolutional neural network. This was a very step forward of convolutional neural networks because it surpassed the rest of the machine learning algorithm. So it's the first time that deep learning actually won a competition in computer vision. 2012, the cat experiment. These are the development of unsupervised learning of deep learning. So they use neural networks spread across 1,000 of computers. The team presented 10,000 unlabeled data, which is randomly taken from YouTube to the system and allow it to analyze on the data. Now, it performed 70% better than the previous attempt at unsupervised learning of all the field, not just deep learning. However, it's only recognized as 15% of the presented object, which is very poor still. However, it's a pretty good result. Now 2014. Excuse me. Oops, I forget to move it. 2014, Deepface and Gone. Deepface is from Facebook. It was a very unique way of solving problem. It's only focused on face of a person in a picture, so it's only focused on the one aspect of the picture, just the face, and it achieved 97.35% accuracy, while human are have accuracy of 97.5, so it's now reached the level of human. Now Gone is very interesting. Again, Gone used two competing network. The first takes the data, attempt to create indistinguishable sample, while the second received both of the data and created sample, and it must decide whether or not the data that's generated from the first network was fake or real. So this is good because now a machine can help each other learn. Ones compete against each other to get to be smarter. So to trick one, trying to trick another, the other one trying to catch the whether or not it's real or false. 2017 DeepMind AlphaGo. It used Monte Carlo tree search. So AlphaGo is deep learning architecture model that's used to that's play Go, which is the popular Asian game. It's pretty popular in Japan, Korea, and China. It's a very complicated game. If you think of chess, it's about 100 more times more complex than chess. So it use value network and policy network. Now it's use combination networks. So policy network calculate probability of winning the game of the position from that current state, which is the, let's say, position 37, 38. Then you calculate towards the end whether or not which of these positions hold the most value or most probability. And then value network is designed to just find a winning probability. So it's try to cut down. These are the networks that on the leaves of the search tree of Monte Carlo search tree. So to cut down the possibility of other searches. These are very successful as well. And in 2017, it won against the world best Go player, which was dominating the field for almost 10 years. So 2018 in August, so it's last month or so, OpenAI won a game against Chinese Dota pro player. So this is not just won the whole game, the whole series of the game, which is consists of 3 games in total. It's won just a game against the Dota team. So even though it take defeat, this is a very complicated game. So let me explain Dota first. Dota is a strategy game. If any of you guys familiar with League of Legends, Dota is a more complicated game than League of Legends. It's more of a you have to use strategies to to get the objective, to win against the enemy team. And it's a 5 players game per team, so there's 10 players in total. Each team have to find ways, strategies to win against other team. So that's why this is our pretty hard problem to solve in general. And okay, so from the picture you can see on the top right here is the GAN picture, picture generated from the GAN. So these are the picture that's generated from the first network. Like I said, these are not the input picture, but the picture that generated from the first layer, and the first network, and the second network has to tell us each one of these which one is real or false, or true or false, which is pretty crazy. And it's the face right here, and then this is the error, top 5 error of ImageNet. This is a competition, and as you can see in 2015, deep learning can surpass human. purple represent deep learning, and blue represent machine learning, and here in Y represent total errors. So it's already surpassed human in vision. And this one right here is AlphaGo, DeepMind. So this one, as you can see, is ELO rank, and you can see that I didn't put the one that show AlphaGo have higher rank than the rest of them now. And Korean now give them the championship award to AlphaGo, which is also interesting. Okay, now why is deep learning important for the future? As you can see, the trend, what I'm trying to show here is interest in deep learning in general on this side, in NIPS growth, which is the vision natural language processing. You can see the tutorial are increasing in exponential amount rate, and conference and workshop also increase in the same proportion. So that's the interest of last year, 2017. And this is here, what I find interesting is that data analytics and big data is the first of the significant technology that's going to be important for each industry, and then cloud computing and so on, and other things. And these three things will the trend is increasing, and these three things are going to push the needs of having sufficient deep learning to deal with all this information and yes, information, sure. So, and also right here you can see that deep learning market is estimated to worth about $18 billion by 2023. Right now, deep learning have a total market of about 3.5 billion. So, in projection, it have to grow at least about 50% a year, which almost unseen in our industry. And these are that you can see that the trend where people start putting more money into machine learning, not deep learning in general, but machine learning. These are types of deep learning. They're feed forward, which is just to feed information and then forward it out. Predict the output. Find the pattern in between, but there's no learn from this error. And radial basis function neural networks, you can see it right here. It's about clustering, so it finds the closest distance from each point, and then make a cluster out of it. So okay, sorry, 1 second. So it's used in power restoration system. For example, there was if the power supply cut off, right, they use this algorithm, for example, to solve whether and rank the priority. If, let's say, a hospital, they try to fix the hospital first, to try somehow to find ways to send electricity to the hospital first, and then try to find and supply electricity to lower priority places. Cohen and self-organized neural networks. This one is unsupervised learning. It is used to produce a low dimensional low dimensional features. Dimensional reduction. There you go. I found a word. Yes, and it different from the rest because it apply competitive learning as opposed to error correction learning, which is more of authorization problem. So they use neighbor function to preserve the topological property of the input space, which means that when one nodes move, the nodes that get to move first, they call it window node, and then they moved in direction of the data that's most alike to the winner, so that when they moved to that positions, when the needle move in that direction, it's going to influence the rest of the nodes to move in the same direction. But the further away from the winner node the other node is, the less the movement is going to affect. So it acts like a gravity in a way. Now, recurrent neural networks, like I said earlier, as STM, they mostly deal with time series because it's memory involved, long-term, short-term memory. They use it a lot in prediction, and also a lot in natural language processing, where you have to understand the word before and after the current word to predict whether or not this word actually means what it is. Because sometimes the machine doesn't understand sarcasm. And then move on to convolutional network. Convolutional networks are networks used for vision and very dominating in this field for a long time. It's so like I said, it mimics the brain, how human perceive image input from the eyes and process that image. Okay, next up we have modular neural networks, which is our field of interest for the future, and there's currently a lot of researcher trying to improve on this network. So the goal here is to the structure is it's a collection of different network work independently and contributing toward the same output of the same data. Each neural network has a set of inputs which are unique compared to other network. So basically what it means is that there's no same set of nodes that connect to the other nodes of the next layer. It may sound like confusing if you don't understand the architecture in general. But then these are pretty good for to reduce the computational power, because the more connected the nodes are between each others, the more time it takes to process. So if you can reduce down those connections to preserve the quality, it's going to be the way forward, because we don't need more data, we only need the right architecture. Then now we're up to another two, variational autoencoder and Boltzmann machine. These two are pretty popular in computer vision again. It is a field of supervised learning. Variational autoencoder are very similar to Boltzmann machine, but I'm just gonna say the shorter word of it, VAE. What VAE do is try to encode the input to lower dimensional of and try to preserve as most of the input data as possible, and then it try to decode it by try to reconstruct the lower dimension to have the same properties or looks of the as when compared to the input data. So it used what they call the encoder and decoder. Now with Boltzmann machine, the difference is that it extracts patterns of the input and then reconstruct the pattern. As you can see here, it doesn't compress the data, it doesn't reduce the dimensionality of the data, it just extracts the pattern right away. Important deep learning architecture. So the first one is CNN, which is convolutional neural network. We already discussed about this, and we know that it is good for image recognition, and computer vision and speed recognition. First one is AlexNet. It is original work of Geoffrey Hilton, who is they say is the godfather of deep learning. No, actually the grandfather of deep learning. There's also a godfather of deep learning and also a father of deep learning, if I'm not mistaken. Getting off the topic here. And first deep learning, it's the first deep learning of its kind that win the competition. And actually it's the first deep learning ever to win a computer vision competition. So that's pretty groundbreaking there. The other one is ZF network net. It's basically a fine-tuning of AlexNet, but what actually make it interesting is another network that used in combination, not used together, just used to visualize learning of the network of the ZFnet. So this picture right here is layer 1, layer 2, and layer 3. You can see the differences on layer 1 and layer 2. You can see the differences of that's the pattern that it detects, and these are the actual pattern in the picture. Same as this is the pattern that it detects, and this is the actual pattern. If you convert this pixel into the real image, you can see. So that's actually the play a big part of helping ZFnet to become very successful. It's a winner of 2013 competition. And the other one, VCCNet. This is the first deep learning. It's the first deep learning architecture. So this one suggests the idea of keep it deep and keep it simple. This is one of the most influential paper or architecture because it what the hell, my brain just shut off. Because it's the first deep learning. It helps the researcher to focus on the right things, the right aspect of deep learning, of what is the way forward. Next one is GoogleNet. It's a winner of 2014 for image classification, and it introduced Inception module. So Inception module is right here. It introduced idea of parallel programming, so parallel processing of computation. So it's kind of just, instead of having just one line that's run, this suggests that you can actually run each layer in parallel and produce a better result. And ResNet is a winner of 2015. It introduced a residual block idea, which is right here. So this idea basically assume that the traditional feed forward may not give all the necessary information to analyze. How about so you can kind of just take information from previous layer and then input into and then add it into the current layer, and then keep doing this. It's also very good for, it's also very easy for deep learning architecture to learn, because it's have like easier parameter to deal with due to this structure. And another one is SENet. It's a winner of 2016. You can see it right here. It's also very interesting because it allows convolutional layer like this one to adapt to over time. This one have a fixed weight or something like that, so where it cannot learn to adapt over time. So it required programmer knowledge to input into it, to kind of just it's a hyperparameter in a way. So this one changed that hyperparameter, converted into parameter, which means that now it can be learned from backpropagation, if you remember. Okay, so now the next one is recurrent neural network. So the first one is fully recurrent networked. It's the most simple of recurrent network. Basically, this is the network right here. So this one is input, hidden layer, and output, and that is the same structure as this, but it can communicate. Right. So feedforward basically just connect every other element in the architecture, but at the same time it also have one feedback back to itself right here. So if you redo this a couple times, you're going to get this. Here we go. And neural history compressor. This one train unsupervised to predict the next input, and only input that generate an error are fed forward. So it's as simple as that. It's only learn things that are errors. So then over time, later on in the time step, so let's say they call this time step 1, time step 2, time steps, and so on. And now later on in time step, since there are less parameters to think about, it have more time to analyze those. And one of the popular one, which we talked about already, is long short-term memory. This is designed to overcome the error backflow problems. Error backflow problem is that when memory of a long term, or memory that happened in a past, in a very long time ago, have affect the future, have impact on prediction. There you go. Have more impact on prediction than those memory that's just recently happened. So what I mean is that, let's say this problem comes from, let's say we are at this time step, right? And then there are some more time step right here of this that have more impact on this time step of the prediction than the more recent one. So that's why it's introduced, long short-term memory. It also introduced gates, which allow the architecture to combine, extract, forget memory or information that it designed for. Now, another one is gated recurrent unit. Now this one it's good when you use with LSTM, so long short-term memory, but it only have 2 gates, which you can see, I think it's right here and right here. You can only have 2 gates. So one of them is called update gate, and the other one called forget gate, refresh gate. Is it? Give 1 second. Reset gate. There we go. So the update gate help the model to determine how much of the past information needs to be passed along to the future. And reset gates decide how much of the past information to forget. And this architecture, gated recurrent unit, allow gates to have its own weight. So you can weigh whether or not this present information or the past information, which one are more important, whether or not you want to choose to forget it or feed it forward. And so this one is like asking question, how much should model learn or forget for each of the layers, which have its own input. Alright, next one is the reinforcement learning. So reinforcement learning is not actual deep learning, but in recent years they are gaining popularity in deep learning, in using deep learning algorithm. So the first one is, before I get to all this stuff, I want to talk about a few things. So about words that you guys have to know to be able to understand what I'll explain on Q learning, DQ learning, and state action, reward state action. So the first one is action. Action are all the possible moves that the agent can take. Agents are the one that's, let's say, learning, and the one that will get feedback from the environment. And before that, so deep reinforcement learning are the learning that is allow reward to be delayed. So then you get to choose action before the reward or respond or feedback got back to you. So then you get to learn whether or not your action is correct in that circumstances. And first, like I said, it was action. Actions are all the possible moves that the agent can take. States are current situation returned by the environment. Reward is an immediate return sent back from the environment to evaluate the last action. Right, like I said, it was reward. And policy, the strategies that the agent employed to determine next action based on the current state. So it is like a rule for taking action, and there will be two more things. They call it off policy and on policy. Off policy are when the agent learn from a policy that doesn't take its own action into account. Not its own action, it shows an action. Like, let's say it shows to do this from when it's in this state, and the policy going to account that action after it's calculate all the reward, and then create the policy to decide whether or not this is a good, bad move. It will sound a little confusing because you guys have never studied about this before, so stick with me. And the value is the expected long-term return with discount. What is discount? Discount represents how much future event lose their value according to how far away in time they are. So it's like decay factors. And so get back to value. Value is the expected long-term return with discount as opposed to the short-term reward. And it defined as expected long-term return of the current state under the policies. So to summarize, value are the value of the long term of the current action of the next action. Let's say you decide to do this. Okay, sure, it may be good for the next move for sure, but will it be good for the long term? You can think of this as, I want to eat this cake. You know, if you eat this cake, you will feel good, but will it make you fat? If it's making you fat, will it make you feel bad about yourself, or your health gone bad? Same thing. Now, another one is Q value. Q value is similar to the value, except that it takes it takes its current action into account. So it's the value that take the current action into account. Yes. So then, so what is Q learning, right? Q learning agent learn policy, which tell an agent what action to take under what states. And this one is off policy agent. So the policy it used for Q learning is called greedy policy. So let's say you get the best out of your action, which of your action will give you the best value, you know. But it has a few problem, right? For a deep Q network, DQN, it tried to eliminate this two-dimension learning, which is, you know, action space and state space, meaning that you only know your next action if you already know the states. So what if you are in the circumstances or states that you have never been in before? Will you be able to adapt? That's what Q learning is not good at. This is the reason why DQN perform way better with a higher dimensional problems. And state action reward state action, SARSA, similar to Q learning, but the difference is it is an on policy algorithm. So it learns from its own action. So basically, yes, it's pretty clear, right? So you learn that you take the current action. The policy is a function of the current action. There you go. Got him. From the input and then try to reconstruct it. Then both of them are going to keep repeat until the error are satisfied before it give, you know, the result. Okay. Now comparing deep learning to alternative options, now you guys might want to know what are the difference, or what are the other options if you don't want to use deep learning. As you can see from this picture right here, you can see deep learning as the amount of data increasing, right? Deep learning perform still better. It's like a log fashion, even though it's not, you know, topped out yet. But okay, and then here's the performance. As you can see here, the machine learning generator stopped right around here before it kind of plateaus. The reason is because classical machine learning often require complex data engineering, and usually they go into do the data analysis and perform those on data itself, and then do the dimensionality reduction to make it less complicated, and then sometimes make an intractable problem become tractable, and then select the best set of the feature before pass over to the machine algorithm algorithm. So first do the cleaning the data, select the data, which is select the features, and then apply machine learning algorithm. And each of the techniques hold potential errors, right? So the more complicated they are, the more errors got exposed to. But in deep learning, you don't have to take care of this. You only have to care about input, clean it nicely. Sometimes you don't have to do it at all. And then you just put it in there, and then it's just going to give you the right option. It's like a black box. That's what they call it in the field. And another thing that's interesting is right here is adaptable and transferable. It's way easier to transfer, way easier to adapt because it can transfer knowledge of pre-existing model of the same, they call it the same domain, to another domain that's have like high overlap between itself and the domain and the previous domain. And this allow less resources to be that's going to be required to perform well. Unlike machine learning, you have to do everything from the beginning, so rebuild it as usual. So what are the benefits of classical machine learning? In what part does classical machine learning do work better than deep learning? It works better on small data. It's true, because there's less data hold less kind of like hidden pattern in there. Sometimes they may not have the same hidden pattern at all, so deep learning cannot find those hidden pattern and solve it. And also it's financially computationally cheaper, because all it does is just like get input, analyze it, and then just put out the output. However, deep learning, it have to keep fixing itself over time until it gets good enough. And yes, now application of deep learning. One thing I want to point out before I want to show you guys, we're going to get into each application, is this picture right here. This picture right here are generated from GAN. So one of the network that we talked about earlier. We just try to learn from it's unsupervised, and try to reconstruct the images that it learns to construct, new image. In this case, it's like an art, So now you can see that deep learning can now apply to art, which you would never thought of. Like no one would ever thought of, really. Transportation, there are effects in a lot of them. Transportation, autonomous car, reduce. If all of the car are autonomous, then you reduce the accident. Number of accident is also reduce cost of the fuel, gas, and also decrease global carbon emission, because you take less time to get to from one place to another place. Now, yes, and also it can use deep learning to find new routes to drive and to save money, as I stated earlier. Now, solving supply chain problem. That's what I was talking about. So supply chain problem are because not everything is connected, so you have to just use the routes that you have. But if everything is connected, find the best path from one place to another and reduce costs, and everyone is going to benefit from this. Healthcare is personalized health monitoring and disease detection. Let's get into disease detection first. Like cancer detection, deep learning is currently a state of art in detecting cancer. And personal health monitoring is that so you can use deep learning to collect medical records and optimize individual medical trail and treatment plan. Now, biology is that analyze biological data or bioinformatics, such as genetic codes, or what you can do is that you can do the DNA engineering. since it's very complicated to understand these genes, how it's influenced the whole growth, for example. Then if you just collect the data of it and then construct deep learning, you can understand how each one of them have the effects on growth. Let's say each one of the DNA or genes, or some of the cells, or some of the disease. Chemistry, so it's optimized chemical reactions. The reactions are almost infinite. There's so many of the molecules and so many possibility of each one interacting to each other. Now, again, hence, it basically means big data. So then if you use deep learning, it's going to solve that security problem. Try to use to detect virus. As the data grow, the more risk, the more virus, the more threats. If you can detect the behavior of virus or threat of spam, you can reduce the risk of getting attacked. Business and finance, you detect financial fraud, because in the fraud, people usually have the same behavior, so they detect those. Predicting weather and market, so like I said, whether complicated big data, use deep learning again. Markets are random, so you can find hidden pattern within there, and hidden pattern may change over time. Perfect match for deep learning. And optimize supply storage, so optimize just supply storage, and other would be Q-learning, so use deep learning with other field of machine learning, in this case Q-learning with reinforcement learning to reinforcement learning, just to get feedback from the environment and improve over time. And IoT is getting larger and larger. More sensors start to gain more of data, produce more data, and then we can use these data to you can learn activity of the pattern of these data, and then understand the relevant behavior of these data. Speech recognition and generation would be from Google Translation. They also use deep learning. From YouTube subtitle, they also use deep learning, or chatbot trying to serve as a customer service. Application of deep learning 1. Feed-forward neural network is most popular from application of its most popular one is from Google autonomous car or self-driving car, and it can also do brain modeling. If you can see the picture right here, not actually the same one right here. Yes, that's the brain modeling. So it's studying how the brain works, so it can so we can understand human intelligence better. And the autonomous car are the example of artificial system building, which is feed-forward neural network. Real basis function neural network. This one is its application would be EEG analysis. So EEG is a test used to find problem related to electrical activity of the brain by analyzing brain wave pattern. So it can detect some of psychological disease that's happened when the brain doesn't function properly, which very interesting. Now, Cohen and self-organizing neural network. This one is using the phonetic typewriter. So what it means is the application is that the model try to type whatever it hear. So then the way it does is the way it works is it recognizes sounds that have like cluster around it. those things can be detected, and it use those to then translate into words by typing it out. Recurrent neural network, as you can see right here, that's recurrent neural network. Now that's predicting like seasonal, they call it. Let's say flight plane. You can predict. Let's say in this time of the year, let's say October, people like to fly. Then go up and then go down at the March, for example, and then keep happening. Now what we're trying to do is detect the seasoning pattern of a flight, number of flight per day in the future. It can also be used in sentiment analysis, speech recognition, and anomaly detection in time series. So pretty clear in itself. Application deep learning 2. Convolutional neural network, image classification, image segmentation, and image detection. There it is right here. I got a pretty cute cat. That one classification say cat. Classification localization say cat, and then box it around it. Object detection, which is a step up in the computer vision. It's like this. So there are multiple objects, and you take all of them. And the other one is segmentation, which is the hardest of them all. You take multiple objects and then kind of like draw a line around it. This is going to be very important in autonomous car, the object detection, and instant segmentation. Modular neural network, MNN, it's still growing research. There was to achieve the abstraction thinking by dividing tasks into submodule, which that's the way how our brain works. We have this task for a small task for each part of the brain. Then once it's finished, it's sent to other places without kind of informing it. However, they kind of still produce the desired result from the input. Fascinating. It can basically do any task that can be divided into simple modules, submodule, which range from like stock prediction. I saw one paper stock prediction in I think 2000s, way back, and you can range it into object detection. And variational autoencoders, VAE, we talk about this quite a bit. Anomaly detection, like I said, it repeats itself over time, and sometimes when you can see the pattern change within this, because what you're trying to do is to encode what's already there. You encode your input, but if you encode your input and then there are some pattern that changes totally, then you can say that that's the anomaly. Another one thing that I find very fascinating is the architecture design. It uses this to recreate the design like aircraft, turbo machinery design. Bozeman machine. It uses topic modeling. So topic modeling is you collect the data and you try to find give me a second. Oh, actually, okay. Topic modeling in natural language processing. Topic modeling is a type of statistical model for discovering an abstract topic that occurred in a collection of documents. So there's a document and detect the topics out of all those documents. It's actually used quite a bit now in businesses. That's one of the most used technology in AI. in the present time business, reduce $1 billion, and collaborative filtering, which is a method of making automatic prediction. For example, about interest of a user from the data you collected, like your preference, and the test of objects or food, for example. And feature learning is you learn the feature, which one is preferred, which one is not. Reinforcement learning, I show you right here, that's a trafficking. So it learns when during the day which one should allow car to run more often and less often, depending on the feedback. And then there's a personalized recommendations and bidding and advertising. And the limitation of this. So let's say that deep learning cannot reason, which is true because it cannot do the abstract thinking, which abstract thinking meaning that it means combination of existing problem to deal with unseen problem. So deep learning are different. It can only solve what's already know, but it cannot combine pre-existing knowledge to solve the unseen problem. Yep. And also, as the challenge here is that as the data grow, sometimes more data is not means better. It means it becomes too complicated to solve. So that's one of the problem with deep learning. And some of the problem cannot be expressed as smooth or continuous geometric of data, which are the kind of domain of problem that deep learning can solve. And deep learning doesn't understand, like I said earlier, it doesn't have abstract thinking. So for example, it's the input is a picture that have it's a picture of a rock that have line. We understand those mean that means that it's a happy rock, but deep learning wouldn't understand that it is a rock in the first place. It just know that this is equal to this number, which is happen to equal to rock, and doesn't even understand the caption here, what's actually happy rock means. And the other point is deep learning can only do local generalization, but not extreme generalization. Local generalization, like I said earlier, was to recognize, as you can see right here, generalized power of pattern recognition. It cannot combine pre-existing knowledge to solve as a problem, which was the case of extreme generalization, which, as you can see right here, achieved by abstraction and reasoning. And I write right here that can't think abstractly, basically mean can't generalize. Now the possible solution from this could be symbolic deep learning, which go back in time before deep learning even become popular. Around that time, logistic people think that the world can be simplified to symbols, and then we can understand those interaction between the environment or the world by just combining symbols. which is totally not the case of deep learning. And okay, now deep learning used the basic of a non-symbolic, which is build computational system that's analyzed input and just match them up. There's no match the pattern up. There's no like symbolic and all that stuff that we have to pre-program into deep learning. And it's right here. That's why even though this is how people understand the world, we have an embodied human experience, abstraction concept, and then data. But machine learning, it can label data correctly, but it doesn't have the abstraction. How can it, understand the real world? And this right here is one of the limitations of the one of the demonstration of why deep learning doesn't understand what it's doing. These two pictures are totally look the same to us, but deep learning wouldn't say it is panda. Both of these are panda. Input are panda is panda, but they would predict this one as gibbon because they add pixel from gibbon class that's most resemble gibbon, and then mix it with the panda image input, and these guys got fooled like that by just switching places of pixel. Now future research on deep learning would be a general purpose computer program is required development of abstract thinking, as we stated earlier, and also the model as program. Okay. By the way, let me just talk about this first. It's one of the research was future research was allowing model to move away from just one type of problem, which is the differentiable problem, and they required less involvement of human engineering. So we wanted the computer to actually learn by itself, not have people to fix it, for example. Now we wanted also to be able to reuse the architecture and make it faster to run. That's we come back to modular neural networks, or in this case it's used as a modular program routine, or meta learning, which is a way to say that a program can learn both parameters and hyperparameters. Hyperparameters are things that cannot be learned by just doing correcting a loss function of the deep learning. So those are the things that's out of control or out of understanding of deep learning. For example, the number of layers, the how deep is the layers, or how deep are how much of the input data you're supposed to put it in, or how many times you're supposed to loop through to get the optimal result. Those are the things that cannot be controlled by looking at the errors and fix it itself. Now we come to the more interesting part, which is model as program. Now as you can see that I think it's the best way to understand is to understand from example, right? So let's say there is we use LSTM RNN, which the short-term memory, which is hard-coded by humans. So we wanted to say, okay, when do we want to use the memory? When do we add this input in, like for example, every 3 neuron or every 3 steps, then we have to add memory in. But how about instead of pre-programming it, we make those become primitive types of model, so it's not like string or no, it's not like string or int like that, but it's more of a collection of things that's going to be the very fundamental of computing or understanding the data. Let's say the loop, we can call it maybe loop parameters, and then we let the loop parameter become learnable from the architecture. Then now the architecture learned to optimize its hyperparameters. Like I said earlier, the short-term memory was pre-programmed by human, therefore it's most likely going to be hyperparameters. So if you do this, if we structure in a way where it's like a program that deep learning can reuse or understand, going to be better. Another point is program synthesis, which is automatically construct program to satisfy given high level specification. So it's going to be better for us, for data scientists, instead of focus on other things in the architecture. They can just focus on the input and output, or what they wanted to do. Let's say they want to solve this, and then they just say, okay, please solve it for me, and then program synthesis is going to create a program that's used to create deep learning, and then try to get the result that data scientists want. So basically, we move away from the detail into more of a wider pictures of the world and how to solve them, more abstract, basically. The other one is, and we can try to do that by using the automated machine learning, which one of the option would be trying to try to create the right program by using reinforcement learning. And the last one is lifelong learning and modular subroutine reused. I already talked about the reuse part, but lifelong learning is basically right here, you can see. So now we have a subroutine for each one, which are the abstraction in a way. Okay, you want to learn abstraction of how to do something that abstract. Can't think of one, how to draw stuff, and then they use this pre-existing knowledge and then use it whenever the task required. So the more we do task, the more pattern we understand, the more of the abstraction we gather, and then the smarter it become. And picture right here is a synthesis gradient, which speed up. It's like modular subroutine reuse, so it's make it faster instead of have to wait for the whole network to run. It can just do it separately. As you can see, each of these layers are not connected per se. It's connected by the M parameter here, but you can see that F is not directly connected, and H represents input data. This right here is well, what you call it again, a synthesis program. Yeah, program synthesis right here. Oops, no, this is also the lifelong learning. My apology. And that is it. This is the reference, and I want to end the presentation right here. Thank you very much. Have a good day.